Hi everybody, we're going to talk today a little bit about sine, cosine, and tangent functions. We're going to look at their graphs and we're going to see if we can come up with anything different about the shape of their graph compared to the other functions that we've been talking about so far. So when we start making graphs and we don't know what the picture is going to look like, we always start by making a table of values, and that's what I've done here. I've created a table of values and I've only done a few of these values. I've only gone up to 2 pi over 3 radians. And then calculated the sine of each of those angle measures. So sine of 0 radians is 0, sine of pi over 6 radians is 1/2, and you can find these exact values from your unit circle or from drawing our special triangles in the correct spot on our Cartesian coordinate system. Remembering, of course, that when we do our special triangles, the radius always has to be 1 for those special triangles. Or you could even calculate decimal approximations for most of these by just putting in sine of 0 radians on your calculator, sine of pi over 6 radians on your calculator, and coming up with these same decimal equivalents, and then plotting those points on a graph so that you can see what goes on. Now, if you do this, and I highly encourage you to do that, you should remember that you need to go all the way up to all of our special angles, all the way up to 2 pi radians, or all the way up to 360 degrees. We want to make one complete circle and see what the sine function looks like. When you do that, you will find that it looks a lot like this. And if you were to continue beyond one circle, past 2 pi, you'd find that it repeats itself this way. And even if you continued backwards, or if you started at 0 and went negative radians around, it would look a little bit like this. Okay? It would look a lot like that. And what you really want to look at here is the pattern that's produced. First of all, we call this length, the distance between the starting point of our pattern and the ending point of our pattern, we call that a period, the period of our function. And we know that since it repeats as we go on beyond that, the period is going to be the length that it takes for one cycle of our graph to show up. In this case, our period is 2 pi. Also, I want you to notice that if you were to pick this up, this side of it, and pick it up and twist it around so that that pivot point was right there at the origin, and twist the whole thing around, this point up here would line up with this point down here. So the sine of pi over 2 is a positive one. But the sine of negative pi over 2 is a negative 1. And when we have that kind of thing going on here, when the sine of an angle, the sine of an angle is equal to the negative sine of the negative angle, we call that an odd function. You can tell that by the symmetry that it has around the origin, how you pick this up and twist it around so that it lines up. So this point lines up on that, and then this point would line up over here. That would give us an odd function. This is the algebra way of looking at whether or not it's even or odd. And then the geometric way of thinking about it is to be able to twist that around and have it line up on itself. Now, the period that we see in our function, the length from the start of the pattern to the end of the pattern, is very closely related to something that we'll talk about later on in physics. And that is the idea of the wavelength, especially a wavelength of waves in the ocean, or wavelengths of light or energy or things like that. So these are very directly related to those very broad concepts in physics. It's really an interesting thing. So we could do the same thing for cosine, but we'll see that when we do cosine, it doesn't start here at the origin. It actually starts up at 1, decreases down to a negative 1, and then goes back up to a positive 1 again. So it still has a period of 2 pi, but it has the same amplitude. I haven't used that word yet. Amplitude is the distance from the lowest point. Actually, amplitude is the distance from the midline up to the top. And but it doesn't have the same starting point at all. So if we look back at the sine curve, here you can see that the sine curve starts here at 0 and then goes up, but the cosine starts at 1 and then goes down. So even though they look very similar to each other, there's a difference between the sine and the cosine. We could do the same thing for the tangent curve. Now, tangent of theta, if you didn't know this before, tangent of theta is equal to the sine of theta divided by the cosine of theta. If you don't believe me, let's just do a quick and dirty little proof of this. Sine of theta, you know, is the opposite side divided by the hypotenuse. And cosine of the same angle would be the adjacent side divided by the hypotenuse. Now, if you've ever done much with complex fractions like this, you know that if you have the same denominator in the numerator fraction that you do in the denominator fraction, you can cross those out and you will get opposite, in this case, opposite over adjacent. That top number will stay where it is, and the bottom number will just stay in the denominator. You'll have opposite over adjacent. And opposite over adjacent is one of the definitions that we have for the tangent of an angle, the opposite side divided by the adjacent side. So that's the same thing as sine over cosine. Now you can get a table of values by taking the sine of theta divided by the cosine theta. You can go ahead on your calculator and just pop in tangent of a particular angle, whichever angle you're talking about on your calculator, and to get decimal approximations. But what you'll find is that when you're talking about tangent, you're going to come up with something called asymptotes. Now, your algebra class, I know you have talked about asymptotes before. Asymptotes always show up when you're dividing by 0. That's one place they show up. So if we're dividing by 0, that must mean that that bottom number, that cosine of theta, is 0 at pi over 2. Is that true? Where is our cosine graph? Well, look here. Our cosine was at its bottom at pi, and it was at 0 at pi over 2. It's 0 again at 3 pi over 2. So do we have another asymptote at 3 pi over 2? We sure do. You know that because I already told you that. But what happens with the tangent graph is that it gets a really different shape than the sine and the cosine graphs. And it's because we're going to be dividing by 0 sometimes. So we get that very, very different shape. It still is repeating itself. Absolutely, we can see that it repeats itself here and here and here. But it doesn't have that same smooth up and down sort of shape that the sine and cosine had. If we want to talk about the range of the cosine graph, or the domain. Remember, domain is going to be all the possible values for what? Possible values for x, I hope you're saying. And the range is going to be all the possible values for y. So if you look here, remember, it's going to repeat itself. Are there any values of x that are impossible to find for, that are impossible to calculate the cosine of? You should say, no, this is always going to be smooth. It's going to go on forever and ever in every direction, and there's no value that I can ever plug in on the x-axis for which I can't get a value on the y-axis. They're always going to be a line. There's never going to be a hole or an asymptote or anything like that. And so because of that, the domain for cosine is all real numbers. What about the range? Remember, the range is all the possible values for y. So if I say, well, what is x when y is right here? I can go and I can say, well, x, one of the places would be right over here. So yeah, I can find a domain value for when that's my value for y that I'm guessing. I can just kind of go right across and come down and say, oh yeah, that's a value that's in my range. But what about if I said, I want to know when is y going to be up here? This is at 1. When is y going to be 2? Does this curve ever go up to when y is a 2? It doesn't. And because the curve, no matter if I put a horizontal line across here, I'll never ever touch this cosine curve. And so that means that there are values where the range does not exist. And if you really look carefully at this, you're going to know that the range, the minimum value for the range is always a -1. And the maximum value for the range is that +1. So the range has to be -1 is less than y is less than 1. Because there are times when we do not have, there are areas on the y-axis where we never ever will be able to touch the curve. Okay. What about for tangent? If we look at tangent, are there places where the domain doesn't have a value, or the places that get us outside of our function? Well, we know that we have these asymptotes, and everywhere we have an asymptote, that's not going to be part of the domain, because these are impossible values for x. So those impossible values for x give us the places where the domain does not exist. And so we see that the pattern for that is actually at at pi over 2, then at 3 pi over 2, and at 2 pi over 2, right? Or we can even go backwards at negative pi over 2 or negative 3 pi over 2. But this pi is the same thing as 2 pi over 2. If you think about it, 2 pi over 2, 2 over 2 would cancel, and we'd just be left with pi. So it's only those odd numbers of pi over 2 which cause us to be outside of our domain. So in this case, we would say the domain is going to be that x, or theta in this case, whichever one you're using, cannot be pi over 2 plus n pi. Now think about that. I want to make sure you understand that. Pi over 2 is this place. Pi is okay, but 3 pi over 2 is not. 5 pi over 2 is not in our domain. So again, pi over 2 is the first one. If we add pi to it, pi over 2 plus pi, well, that's the same as saying 2 pi over 2. That's going to be 3 pi over 2, and we know that's not in our domain. Or we could say pi over 2 plus, if we didn't want to say pi, we'd say 2 pi. But we can't add unlike denominators, so 2 pi actually ends up being 4 pi over 2, which would end up being 5 pi over 2. Excuse me. So when we use this formula for our domain here, n can be any integer, positive or negative, and this will give us a definition of all of the places where the asymptotes are going to show up. What about our range? For the tangent function, is there any place where we do not have a y value? Can I draw a horizontal line anywhere and come up with a place where it does not cross the function at least once? Nope. The range for the tangent is all real numbers. Okay. So now we can talk about domain and range of all of our functions. We've talked a little bit about how sine is even. What about the tangent function? Would the tangent function be even, or would it be odd? I sure hope you said odd. And you can prove it algebraically. I'll let you do that on your own. Or you can look at the graph and say, oh, but if I pick this thing up and rotate it around, this part of it's going to, sorry, get my pen out of the way. This part of it here is going to rotate around to end up just on top of there. And because it's going to rotate on that pivot point, because it's going to be reflected across the origin, it has to be odd. What about cosine? Is the same thing said for cosine? If I cut this half of it and rotate it around the origin, will it end up on itself over here? No, it won't. What kind of symmetry does it have? Is there any? On this one, the symmetry is going to be across that y-axis. You could actually fold it, not rotate it, but you could fold that graph so that this folds up on top of that. Again, this part of it will fold up over onto that part over there, and then it will line up. It will have symmetry that way. And when you can fold it into symmetry across that y-axis, then we say that it has even symmetry. Not odd, but even. So sine and tangent are odd, and cosine is even. Okay.